everybody. Our guest speaker is Professor Jorge Pullin. He's well known here, so that I don't need to introduce him. The title of his talk is Conditional Probabilities with Evolving Observables and the Problem of Time in Quantum Gravity. George, please begin. The audience is yours.
Okay, thanks a lot for the invitation, and thanks for accommodating changing the time and waiting so late on a Friday for me. I'll try to be as brief as possible so you can go home. Well, you are home, but at least go back to your families and so on a Friday evening. So this is work we did with my collaborator of many years, Rodolfo Gambini, which I understand spoke to you relatively recently about the more philosophical aspects of this that he sort of likes. I'm not as knowledgeable about those aspects. And two of his former students, Sebastian Torterolo and Rafael Porto, who is now a staff member at DAISY in Germany. Okay, so you all probably have heard about the problem of time in classical and quantum gravity. There is extensive literature. There's a very comprehensive review by Karel Kukash that I recommend. It's really well written and really touches all the points. I'll briefly recap on what the problem is. The heart of the problem is that Einstein's theory is what is known as a totally constrained system, meaning that the Hamiltonian is a combination of constraints and therefore has to vanish. Since observable quantities in systems with constraints have to have vanishing Poisson brackets with constraints, they have, as a consequence, vanishing Poisson brackets with a Hamiltonian, and therefore do not evolve. We are going to propose a solution to this, but before that, I'd like to discuss two previous proposals. There have been many, many proposals over the years to deal with this problem. I'm not going to review all of them. Again, Kukash's review is really good. But I'm going to review two of them because we're going to combine them to propose our solution. Both these proposals have in common that they are relational. And in fact, it's a common ingredient in all these proposals to try to introduce a notion of time to have relations between the degrees of freedom in a theory. The first proposal is the so-called evolving Dirac observables, also known as evolving constants of the motion. Carlo Rovelli has been emphasizing this over the last few years, but in various different ways and forms, the proposal has already been, you can find glimpses of it in the work of Peter Bergman, Bryce DeWitt in the 1960s. And the second proposal is the so-called conditional probabilities approach that was proposed by Page and Wootters. We will see that both of these approaches, in our opinion at least, do not provide a completely satisfactory solution to the issue of evolution. And the problems are particularly acute when you try to compute propagators or to assign probabilities to histories. And we will see that a combination of both approaches seems to address the problems they present. So let me discuss the first of these approaches, the evolving Dirac observables in totally constrained systems. So in a totally constrained system, the action is like this, is PQ dot minus, and where you normally have H, the Hamiltonian, you have a bunch of Lagrange multipliers times a bunch of constraints. So when you take the variations of the action with respect to the Lagrange multipliers, you get that the constraints vanish. General relativity is a particular case of these theories. One can write general relativity like this when one formulates it canonically. And in general relativity, the constraints are first class, meaning if you take Poisson brackets of two constraints, you get a combination of constraints. If your constraints are not first class, there are things you can do to deal with them, but I'm not going to enter into that because the case of interest, which in general relativity is first class. So that, as we were saying, the Hamiltonian, the total Hamiltonian of the theory, is just a linear combination of the constraints. And so the generator of evolution, the Hamiltonian, also generates the gauge transformations for the theory because it's proportional to the constraints. Dirac observables are quantities that have vanishing Poisson brackets with the constraints. And as a consequence of this, they also have vanishing Poisson brackets with a Hamiltonian. And one gets what is known as a frozen formalism. The observable quantities do not evolve. So if physically relevant quantities in these systems are constants of the motion, how can we describe the evolution? So the first of those two approaches I was mentioning is these evolving Dirac observables, or evolving constants of the motion, as Rovelli calls them. And the idea is that these quantities are the evolving constants of the motion. They are Dirac observables, meaning they have vanishing Poisson brackets with constraints, but they depend on a parameter. Okay, so they're a Dirac observable that depends on a parameter, and as a Dirac observable has vanishing Poisson brackets with constraints. And they have the property that if you evaluate that parameter on one of the canonical variables, the value of the Dirac observable is one of the canonical variables. Okay, so this is the essence of the construction. And, spoken like this in the abstract, this sounds very abstract. So let me show you an example how this works to see that it's very simple. We take the parameterized relativistic particle. So you take a relativistic particle in which you introduce as canonical coordinates time and its canonically conjugated momentum, the energy. So this would be the energy, the conjugated to x0. And the constraint is the mass shell. So this is the condition of mass shell, energy equals v squared plus m squared. One can write many different independent observables, but here are two. P is an observable because it obviously commutes with this. And this other one called x that is defined here, that is a little bit, it's one line calculation to show that this also has vanishing Poisson brackets with that. If we define now our evolving constant of the motion to be this, to be x plus this quantity, this is a Dirac observable, as you can see, because it's a combination, it's a combination of these two Dirac observables, not a linear combination, but a combination, and a parameter t. And if you substitute q0 here in t and substitute x, you get back q. Okay, so we have reproduced this construction here. So what Rovelli and others would argue is that this is one way of introducing a dynamics of the theory. Your Dirac observables now have a time dependence, a dependence on this parameter. This parameter would play the role of time. What is the problem with this construction? Well, the problem with this construction is that this parameter t is a parameter. That is not supposed to be quantized. You're not supposed to put a hat on top of it or anything like that. But at the same time, you have to enforce this condition here. And q is one of your canonical variables now that normally when you quantize, you promote to an operator. So what do you do with that parameter t? What do you do with the condition q0 equals t when t is a parameter and q0 is a quantum operator? Well, there's no clear answer to this in the literature. One possibility would be to put expectation values here, but then the construction isn't what you had before. And the evolution that you get is not going to reproduce in the classical limit, the classical evolution. The problem is even worse if you're in a theory with constraints, because in a theory with constraints, of course, the canonical variables are not Dirac observables. If you act on the space of physical states, this will not be in the same Hilbert space as this. This will take you out of the Hilbert space. So this issue is unanswered in this approach. There is no clear way to handle this. So that, in our opinion, is the problem with this first approach. Let me go on to the other approach, the one of the conditional probabilities. So the second alternative is to consider the description in terms of conditional probabilities. This is what Page and Wootters propose. The idea is you take all your variables in your system and you promote all of them to quantum operators, and then you compute conditional probabilities between them. The idea actually appears very simple, natural, and attractive in a closed system. You might say, well, but these variables, what variables are you actually going to use to do this? And that is the problem of this proposal. If you're in a totally constrained system like gravity, which variables are you going to use to compute these conditional probabilities? If you use Dirac observables, they don't evolve. So to ask, what is the conditional probability that some variable takes a value when some other variable takes a value, if this variable never evolves in any sense, it's not going to give you anything that looks like a regular quantum probability. It would be like, I don't know, using as your clock variable the position of a rock that is just sitting there. That is not going to lead to any evolution that you'll distinguish as a traditional evolution of a quantum system. Page and Wootters were, of course, acutely aware of this, so they proposed, no, don't do that. Use your kinematical variables, your canonical variables if you want, and compute relational probabilities between them. There is some sense in doing that because although the variables themselves are not Dirac observables, and therefore you're not supposed to ask questions about them in a constrained system, the relations between them do have observable nature. That is, to say what is the curvature at this point is not a well-defined quantity thing in general relativity because the point is not a well-defined notion. But if you were to say, what is the value of the curvature at a point where component 2,3 of the curvature is 3, that statement would have invariant meaning because you're labeling the point with a physical variable of the theory. So they said that was their proposal. Unfortunately, when you look at the details of doing that, when you have to compute the conditional probabilities, you have to take expectation values. And when you take expectation values, you have to put quantum states. Now, what quantum states are you going to put there? If you put kinematical quantum states that are not solutions of the constraints, where are you putting information about what theory are you working with if you're not using the constraints at all? You can't do that. If you want to deal with the theory you're dealing with, you'll have to put physical states, states that are annihilated by the constraints. But the variables that you're taking expectation values in between are not Dirac observables. So you're back at the previous slide. That variable is going to take you out of the Hilbert space. And when you take the inner product, that inner product will be ill-defined. Karel Kukash, in his review for the problem of time, applied this idea to a system very similar to the one we discussed before, the parameterized particle, but instead of taking one particle, he took 2. So you could use the position of one particle, say, to be your clock, to study the position of the other particle. And what he found is when you compute the conditional probabilities the way Page and Wootters suggest, instead of getting the usual propagator between t and x, t prime and x prime being the correct propagator, you get that the propagator between t and x and t prime and x prime becomes delta t minus t prime, delta x minus x prime. The distributional nature of the solutions of the constraints is what forces the appearance of those Dirac deltas. And what it means is the theory does not propagate. It's a particle that never propagates. Okay, if you had a tx prime, t is equal to t prime and x equals to x prime. And he worked this out in detail, and therefore this proposal doesn't lead to the correct propagators. So what are we proposing? We're proposing to combine these two approaches, that is to compute conditional probabilities like Page and Wootters suggested, but instead of using kinematical variables to compute the conditional probabilities, we use evolving constants of the motion. We use genuine Dirac observables, but that depend on a parameter. So both approaches up to now require the use of variables which are not defined on physical space. And here we would like to use a different approach where all reference to external parameters are abolished and evolving constants are used to define correlations between Dirac observables of the theory. The proposal was written in detail in this PRD in 2009, and I'm going to refer to you to many of the details there because I just want to give you the general idea of the proposal in this talk. So we, as I was saying, we revisit the Page-Wootters construction by computing relational probabilities between evolving Dirac observables. These are Dirac observables, so they're well defined on the physical space of states of the theory, and they're quantities that one expects to observe and be represented by well-defined self-adjoint quantum operators. So we carry out the proposal of Page and Wootters. We choose a variable that we're going to call the clock, capital T. It's a Dirac observable, and it depends on a parameter that is going to be unobservable in our theory. And then you pick whatever you want to study, a bunch of other Dirac observables, also dependent on a parameter. These are all evolving constants of the motion. And you compute this. So I do the condition, this is the conditional probability, there's a little vertical bar there. Probability that an observable take a certain value. The reason I use an interval here is because most situations you're dealing with variables that have a continuum spectrum. You can't ask when you have a variable with a continuum spectrum, what is the probability of an exact value, because you get 0. You need to ask about a little interval. So what's the probability that whatever I'm studying, my observable takes the value O0, or is in this little interval around O0, conditional on the time being, I don't know, 10:15 a.m. T0 would be 10:15 a.m. And this is the usual way to compute that. You take your state, your density matrix, and you hit it with projectors on the eigenspace associated with this eigenvalue. So this projector associated with this eigenvalue on the eigenspace associated with this eigenvalue, projector associated with this eigenvalue, and you hit it on both sides, the usual way, because the trace is cyclic. You can take the P of O0 that you have here, bring it to the other side, and see these are projectors, their square are equal to themselves. And that's the reason we have only one of this on the other side. You can't do this with the other one, because if you bring it here, you can bring it here if you want, but it's not going to annihilate. And the conditional probability means there is this denominator here.
Yeah, excuse me, George. How is exactly this small t defined?
So this small t will be my parameter of the evolving constant of the motion that I constructed. So for instance, if we were looking at the example of the particle I introduced before, that little t appeared there explicitly when I constructed my evolving constants of the motion.
So it is not observable.
It's not observable, it's a parameter. And notice that on the right-hand side, we are integrating along all possible values of the parameter because we cannot observe it, okay?
Okay, thanks.
So t is the parameter associated with the variable used to define the evolving observables, and it's treated as an ideal quantity that we, in this construction, do not need to observe. In that PRD that I mentioned there, we showed that if you apply this construction to the model that Kukash studied, the two parameterized particles, you actually get the correct propagator. Calculation is a little bit lengthy to show in a talk. It's not hard at all. I refer you to the paper if you want to look at the details. I'd like to prefer to invest the rest of the talk to show how this makes contact with things you're more familiar with. That is, presumably, I could apply this construction anywhere. It doesn't have to be a constrained system like general relativity. I could apply this to an ordinary system in quantum mechanics. Does it lead to ordinary quantum mechanics, or does it lead to something else? Okay. So how do we make contact between these probabilities we're computing there that look, they look abstract, they look complicated, etc. How does the Schrödinger equation fit in here, for instance? Can I get the Schrödinger equation from this if I apply it to a non-relativistic particle? So that's what I'd like to address. So say you take an ordinary quantum system, forget general relativity, forget constrained systems, we just ordinary quantum mechanics, okay? Some system you want to study in the lab. How do you apply this construction? Well, first you choose some variable that you call the clock, okay? And you call it t. Notice that t is a quantum operator, okay? So a variable is going to be promoted to a quantum operator in all cases. In the case of a constrained system, it will be a Dirac observable, parameterized Dirac observable that you can definitely promote to an operator like all Dirac observables. Then you choose whatever variable you want to study. Let me call that variable x. Again, this will be a quantum operator. And then you'll compute the conditional probability that we had before. And here I just omitted the intervals because I discussed the issue before. Strictly speaking, this expression here will only be true if x0 and t0 have a discrete spectrum. If you have a continuum spectrum, you have to ask about little intervals. But just to make the expression simpler and easier looking, I just wrote it this way. And you compute what you had before. If you have an ordinary quantum system in like ordinary Schrödinger theory, then this t will be what normally we call time. It will be the classical parameter that appears in the Schrödinger equation. That if you had a constrained system, it would be the parameter of the evolving constant of the motion. And you compute, sorry, this x should be capital here. It's the same x as there. And you compute these probabilities. And we think here we're in the Schrödinger, in the Heisenberg picture, where the operators evolve with time and the states do not. But of course, you can do the calculation if you want. In the Schrödinger picture, then the operators would not evolve with time and the rows would. That is, this is the conditional probability that whatever I'm studying takes a certain value x0 when the variable I chose as a clock says 10:20 a.m. On the right-hand side, t will be the ideal time of the Schrödinger theory. And as I said, in the Schrödinger picture, the density matrix will evolve with time and not the operators. And let's see how the usual Schrödinger evolution would emerge from this. So how does the evolution look like when one writes it in terms of this big T, which is a quantum operator, instead of the idealized Schrödinger T? Here we need to make some assumptions, okay? The Schrödinger equation is going to emerge in certain limits. Obviously, the limit in which the clock you take is a reasonable clock. If you take your big T to be an operator that is jumping all over the place in a very quantum fashion, you will be able to write an evolution in terms of it, but it's going to look very different to ordinary quantum evolution, because the ordinary quantum evolution is framed in terms of a variable that is evolving, you know, monotonically, semi-classically, etc. So if you want to see the usual form of quantum mechanics, you're going to have to pick a clock that behaves the way clocks behave in ordinary quantum mechanics. So you need to pick a sensible clock, and we'll also assume that the clock and the system don't interact. You don't have to assume this. You can have a clock that interacts with the system. It's just that that's not the ordinary situation. I'm trying to get as ordinary as I can now to make contact with ordinary quantum mechanics. And in ordinary quantum mechanics, you don't have clocks that interact with the system, okay? If you add interactions between the clock and the system, you can do that. You'll have additional terms to the ones I'm discussing here. So I'm going to assume that my density matrix is a direct product between the one of the clock and the one of the system, and that the evolution operator is also a direct product. So the clock evolves by itself, the system evolves by itself. Again, this is what one normally does in ordinary quantum mechanics. I'm trying to recover that, therefore I'm making the usual assumptions. You don't have to do any of this. The previous expression is true in general for any variable x and any variable t. It's just that if you pick weird t's and weird x, the probabilities you get, they're well defined. Well, generically, they're well defined. There'll be cases where these integrals blow up and stuff like that. You have to worry about all that. But assuming the probabilities are well defined, they'll exist, but they're not going to behave in any way that you recognize easily. Okay? So that's what I'm trying to do. I'm trying to boil down this to a situation that one could recognize. So we make this assumption, and we also define this new probability T. Let me explain a little bit what this is. So this is the probability that the quantum variable T take a value when this idealized variable T takes a value. So what's the probability that this is 10:15 when this is 9:30 a.m.? These probabilities are not observable physically because they depend on that parameter that I don't know its value. But certainly I can write them down mathematically. No one prohibits me from writing this down. And I'm going to use these probabilities to label my quantum states using the big variable T in this way. So this would be rho of little t, the usual Schrödinger sort of evolution of my density matrix, rho of t here. But I'm going to multiply it times this probability, and I'm going to integrate over all t's. And that's why I'm going to define this rho of big T. Now, if this t was able to perfectly tract this little t, then this probability would be a delta. It will be a delta of t minus big T. And then the evolution of this would be equal to the evolution of this. The integral would take away the delta, and I would get the usual Schrödinger evolution. But generically, this will not be the case. Generically, this big variable T, even if I choose a clock that behaves very classically, monotonically, etc., it is still a quantum variable, it will have some uncertainty, and it won't be able to track completely accurately what a classical parameter like t does, like little t does. So generically, this probability,
which variable are involved in trace? Which trace is calculated over which variables here?
So this is an ordinary trace in quantum mechanics. This is my
It's on, for example, for single particle, it's only over this position variables or what?
This is a trace over the quantum state, right? So this will be a matrix in general. These are operators in general. They're all matrices, and that's what the trace means. We're taking an expectation value, essentially. That's all we're doing.
Yes, this is true, but trace, in fact, is related to scalar product.
Right.
Scalar product is also related to variables which parameterize your system.
Right.
So that is in this sense is a question over if all variables are used here. On the left-hand side, you have a number, in fact.
Right. So the left-hand side is the number, definitely.
But you assume that it might be another letter. I don't see it on the screen exactly, but it on the left-hand side is number, is probability, or it's only it's also a projection operator which you are using below.
No, this is just a number. This is
number,
not a projection.
Simply number. It's probability. This related probability, not?
Yes.
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 Okay.
So as I was saying, if I could construct a perfect clock that perfectly tracked little t, this would just be a Dirac delta. So that this is always a number that usually is peaked. If you try to make your clock reasonable, this big T will sort of have values peaked around the value of little t, okay, or displayed.
Okay.
I don't know.
Because I noticed that it's not the same p, but on the screen it's not well seen.
Okay.
Mm-hmm.
Okay. So with these identifications, one can go back to this expression here and rewrite it in the following way, which is the usual expression in ordinary quantum mechanics for the probability of observing a variable at a given time. So we have reconstructed ordinary quantum mechanics in terms of this big T variable. So how do these probabilities evolve? Do they evolve exactly like in quantum mechanics? Well, to do that, again, we need to make assumptions about our clock. And as I said, I'm going to assume that our clock is a pretty good classical clock, okay? So my variable t is going to track pretty close little t, but not quite, okay? So this is what I was saying before. If my clock was perfect, this would be a Dirac delta. But I'm going to assume that my clock is not exactly perfect because there is no quantum variable that can track precisely a classical parameter. I'm going to assume there's some corrections to it. They're small, okay? They're also of the sort of Dirac delta. So this is basically a distribution that is very peaked, but it has a width and has a first moment there. Now, if you stick this P in the definition of rho that we had in the previous slide, and you expand things out, you get that the evolution takes this form. And I'm keeping here only up to this second term. Generically, of course, there are infinitely many terms here, and there'll be infinitely many terms in this expression. But I just keep the leading one to try to understand what is the effect of it. As you see, these commutators with a Hamiltonian appear. And if you translate this into a Schrödinger type evolution equation, so this would be the Heisenberg type equation of evolution for the state. If you want to translate it into a Schrödinger equation, you get an equation of this form, where this sigma that appears here is the derivative of B. It turns out that this first term, the one that just displaces the variable, has no effect on the evolution. It would be equivalent to adding a T0 to your clock, okay, to using a clock that is just shifted in time. So that doesn't change the evolution at all. The first non-trivial correction to the evolution comes from the width of your distribution, the fact that your distribution has a width, and its time evolution. That is, this b of t here gives rise to the sigma. Sigma is dB dt. So if your evolution is spreading, then you get this correction to the usual form of the Schrödinger equation.
Excuse me, on the previous slide, you have this trace over rho in the denominator.
Yes.
To which value or how it is normalized, this density operator?
Right,
so this trace is not 1.
The trace, you can take it to be 1 if you normalize the states or not. Generically, therefore, I left it in the denominator. Otherwise, if it's normalized, it's just a 1.
But it's, you say that it's finite. This trace has to be finite and normalize it arbitrarily.
Right.
Yeah?
Exactly. Okay. And I'm missing a parenthesis here, sorry.
It doesn't matter.
This equation here is a particular case of an equation that is known. The similar equations to this arise in the context of decoherence, and they're known as Linblad equations. But this is a particular case of the Linblad equation. The Linblad equation in general has another operator here called D, they call it in the decoherence language. So this is just a particular case of the Linblad equation where that operator D is the Hamiltonian. This, by the way, is good because it implies that this equation conserves energy. Previous proposals for loss of coherence due to quantum gravity, like Hawking's dollar matrix and Andy Albrecht's proposals and others, ran into problems quickly because they were not conserving energy. Those problems here are avoided because of the particular form of the equation that emerges from this construction. So as I was saying, sigma of t is the rate of spread of the wave function of the clock. And we assumed, as we did in the calculation in the previous slide, that we're in a clock that has a distribution that's very peaked. So my variable t tracks pretty well the little variable t, and therefore the Schrödinger, traditional Schrödinger evolution arises at leading order. If you don't do that, if you have a wild distribution, you get, first of all, infinitely many terms here. You always get infinitely many terms here, but I just chose things carefully such that the other terms are smaller. But if you don't, all the terms will be there, and this will be a mess of an expression, and you won't recognize the Schrödinger, traditional Schrödinger evolution there, because you'll be asking questions about probabilities that are very different from the probabilities you normally discuss in Schrödinger's theory. So what are the consequences of that extra? And I emphasize, generically, you have infinitely many terms, okay? I'm only going to concentrate on the first because it's easy to analyze, and it leads to interesting effects. The other terms will imply additional effects. So if we assume sigma is constant, this equation can be solved in closed form. So sigma equals constant means your rate of spread of your state is constant. So what you get is that the solution of the equation is like this. The density matrix evolves in this form. This is the density matrix in the energy eigenbasis. So N and M are sort of labels of the energy eigenbasis, states of energy. And you get that the evolution is this. This would be the traditional Schrödinger evolution, where omega and M are the Bohr frequencies, taking h bar equals 1. But there's an additional term here that is different from the Schrödinger evolution. And notice that the extra term is not of unit form. This extra term just has a minus sign here. So this is negative definite because these are squared and this is positive. And what this means is that the off-diagonal elements of this matrix, where n is different from m, because the diagonal ones have omega is equal to 0, so this term just is 1. But for the off-diagonal terms of the density matrix, they decay exponentially to 0. So the off-diagonal elements decay, and pure states generically evolve into mixed states. So quantum mechanics with real clocks, therefore, does not have a unitary evolution. I'd like to pause for a second here, because a lot of people, when I say this, get very upset. They say, look, unitarity is fundamental in quantum mechanics. How could you violate that? What are you doing here? Okay, so let me argue that this that comes out here is really trivial, if you want. It's nothing profound. It's something, you can say, stupid. It all goes back to this definition here. This rho is the usual Schrödinger rho, evolving with the usual Schrödinger time in the usual form. This would be rho of t. These t would be rho of t. That is evolving unitarily. If you look at my hands, this evolves unitarily. Ordinary Schrödinger evolution, nothing funny going on here. Now, this rho, because it has this probability stuck in there, and this probability generically is not a delta, it has a width, it means that as this little t is advancing unitarily, this big T is sort of hesitating. It doesn't know when this one says 10:35 a.m., this one might think it's 10:34 or 30:36. And that is the loss of quantum coherence we're getting. We're losing coherence, although the evolution is unitary underlying the whole thing, we're losing coherence because we're using a lousy clock to track it. It's a statement as trivial as saying, if I use lousy instruments, the laws of physics don't look right. That is what I'm doing here. I'm using a lousy clock that cannot track the ideal clock perfectly, and that leads to a loss of quantum coherence. That's all that is going on. So even if you're doing ordinary Schrödinger quantum mechanics, forget constrained systems, forget the evolving constants of the motion, if you choose to phrase the theory in terms of these types of real clocks, clocks that are associated with quantum operators, that have uncertainty, that have dispersion, you're going to lose unitarity, because no quantum variable can perfectly track the T that appears in the Schrödinger theory. That's all I'm saying. As you see, it's a fairly trivial statement. It's not something profound or weird. I'm not modifying quantum mechanics at all. Underlying this is Schrödinger's theory for an ordinary system, for a regular non-relativistic system. It's just that I'm choosing to phrase the theory in terms of variables, in terms of which its unitarity is not apparent. Now, on the other hand, any clock that you have in your hand in the lab, be it digital, be it whatever, is like a big T, is not a classical parameter, is a physical system. Its value will be the result of a quantum operator, no matter how classical your clock is. So as we were saying, we lose the unitarity in the evolution. A question you might have is, well, has this been observed? I mean, presumably, it would be easy to pick a lousy clock, do an experiment in the lab, and see that this happens. Well, surprisingly, experimentalists don't pick lousy clocks usually, right? So we had to look for a while to find an experiment that actually represents this in a sense. And this had actually been identified by other people, that it wasn't us who found this. There are these experiments they do with Ravi oscillations, where they take rubidium atoms and they shoot them into a cavity, and these atoms have two eigenstates they can be in, and the population of atoms that is in one eigenstate or the other, as it travels through these cavities, exhibits these types of oscillations known as Ravi oscillations. Now, this is actually experimental data, and as you see, the oscillations are not perfect. They have superimposed on them decaying exponential. The reason for this, and this is the reinterpretation of Bonifacio and collaborators, is that they're using a lousy clock to do this. What do they mean by that? Well, how do they know how long one of these particles lives in the cavity? Okay. They know it because they know the length of the cavity and they know the speed they shoot it in with. How do they know the speed they shoot it in with? Well, because they prepare them at a certain temperature. Now, the particles at a certain temperature, of course, don't have a monolithic single speed. They have a Maxwell distribution of speeds, okay? So when they say 40 milliseconds or 60 milliseconds, they're not saying it accurately, because they're shooting particles that are going to be there 40 milliseconds, 39, 41, according to the Maxwell distribution. So essentially, they're using a lousy clock. And what Bonifacio et al. Noticed is that this decaying exponential that they have on the Ravi oscillations is the manifestation of this factor here. So indeed, if circumstances force you to use a lousy clock to do quantum mechanics, you do see this loss of coherence. The formula for the Ravi oscillations of ordinary quantum mechanics says that the oscillation goes on forever. It doesn't have an exponential decay. The exponential decay comes because you're not using the time, quote unquote, of ordinary quantum mechanics. You're using a lousy clock. By the way, the experimental data are not from Bonifacio, they're from this group, Wineland's group in the US. And of course, these people don't explain things in this language. They are well aware of what is going on in their cavity and that the particles don't enter all at the same time. They explain it that way. They don't say we have a lousy clock, but in fact, that is what they have. So you say, okay, fine. There is this effect, I grant you. I understand what you're saying. If you use a lousy instrument, the laws of physics don't look right. But can't I just use a better instrument and make this effect go away? Can I always go and buy a better clock? And the answer is no. You can't buy an arbitrarily accurate clock. There are fundamental limits on how accurate a clock can be. And there's been, so the question we want to ask here is, what is the best clock we can build? That is there a lower limit to this effect beyond which I cannot eliminate it? That is, will I have a fundamental loss of coherence that I cannot do away with no matter how hard I try? Well, there's a long literature on trying to answer the previous question, namely the question, what is the best clock we can build? The first to address this was Wigner with his collaborator Saliker. Wigner was the president of the American Physical Society. And you know, when the president finishes his term, they make a speech. These days, the speech is about, you know, some political thing or global warming or something like that. But in the time of Wigner, the speech was about physics. And he made a speech about how accurate could you make a clock. And with Saliker, what he explored was a clock that was so ideal that it was completely isolated from the exterior world. And therefore, the wave functions of the parts of the clock would start to spread. You see, ordinary clocks, their parts do not spread because they interact with the air and everything, and there's decoherence all the time going on. But even if you eliminate all those effects, you have a fundamental effect, that is that your clock starts to spread. And Saliker and Wigner noted that that spread was inversely proportional to the mass. So if you wanted a clock that lasted longer, you had to make it more massive. But then came Jack Eng at North Carolina and argued, well, you cannot go that indefinitely, because if you make a clock very massive, you form a black hole. Now you say, well, couldn't you make the clock very massive or very big? No, because if you make it very massive and very big, you don't form a black hole, but big clocks are also inaccurate because you run into speed of light sort of limitations. The various parts of the clock have to communicate. And there are various variants of this argument one way or the other. There are many people that have been involved in this. And they all more or less reach the conclusion that there is a fundamental uncertainty in a clock that you cannot go beyond that is proportional to the Planck time. Now, the Planck time, of course, is 10 to the minus 44 seconds. It's a ridiculously small time. And for all practical purposes, yes, you'll lose coherence, but the rate of loss will be so slow that you'll never observe anything of this. But what's interesting of these formulas that they find is that it's not proportional to the Planck time, but a fractional power of the Planck time. And it is proportional to a power of the time you're trying to measure. So the times you usually try to measure when you write them in Planck times are large. So this is a large number. So if this were 1 second t I'm trying to measure, t in Planck units would be 10 to the 44. Now 1/3 of that is still 10 to the 14, 10 to the 15. So this is 10 to the 15 sort of Planck times. So that makes this effect a little bit bigger. I'm not going to give you a detailed analysis of this because they're hand-waving calculations. The essence of the calculations are what I told you. They combine the Saliker and Wigner estimate with other limitations coming from gravity. You either form a black hole or something like that that prevents you from building a clock. And they don't all reach the same conclusion for the powers that are involved here. But the important thing is that in all cases, the spread of your clock is time dependent, and therefore that sigma that we had in the previous equations is non-zero. That is, if the spread were constant, then the evolution would be unitary. But as long as you have a time dependence in it of some form, of this form here, A again, as I say, different authors, Amelino Camellia has a different value than others, and so on. It doesn't matter. As long as you have an A bigger than 0 here, there will exist a fundamental loss of unitarity. And we discussed that in some detail here. For those of you who are into these things, you might know that there has been some progress in the problem of time and quantum gravity done by Philip Huynh and collaborators using POVMs, positive operator valued measures. And we have recently reformulated this whole approach in terms of the language of Huynh, and the results still go through. So it's satisfactory that with these new tools that people have included, one can update our calculations and the main results of the loss of unitarity still hold. So let me conclude here. So using the first message of the talk was using evolving constants of the motion like Rovelli does in the construction of Page and Wootters allows to correctly compute the propagator and assign probabilities to histories, at least for the little example that Karel Kukash had worked out of two particles parameterized, where you use one to be your clock and the other one you study. It is very difficult to make, so this is a very general statement, very grandiose statement, but I want to humble myself and tell you, we only did the calculation for that very little simple constrained system. The calculations get messy when you want to go on something more realistic like quantum gravity. I think it was completely possible. If you wish, you could, for instance, consider homogeneous cosmologies, consider two scalar fields coupled to homogeneous cosmologies. So I use one as a clock and then study the remaining system, a scalar field with a Freeman universe, and you'll be able to reproduce the usual results of quantum cosmology if you want to do them with loops of loop quantum cosmology with this framework. No one has done that calculation yet, but I'm completely confident that that calculation can be done. If you want to do it for quantum gravity in general, then you're going to run into all the problems that we don't know how to write Dirac observables for the full theory and full generality, etc. And the technical details will inevitably get in the way. Conceptually, the construction is there. Doing it is a different story. The resulting description that we got, as you saw, is entirely in terms of Dirac observables. The non-observable parameters that are involved in the construction are integrated away. You never need to assign them a value based on physics. They're just a mathematical part of the construction. There are corrections to propagators due to the use of real rods and clocks. By the way, if you were doing quantum field theory, you not only have to do this kind of construction for your clock, you have to use similar constructions for measuring special spatial distances. We actually have a little paper where we did a first exploration of that. And there's a very similar loss of coherence in space because your measuring rods are not the X that appears in quantum field theory. In quantum field theory, your quantum state would be a function of T and X. Now your labels would be a big T and a big X, a big real clock and a real rod that you use to measure space. And you'll have loss of coherence due to both of them, due to the fact that your real clock cannot really track the little t that you would have in ordinary quantum field theory, and that your big X, your real rod, cannot track the little x that you would have in quantum field theory. And so you would have a fundamental loss of coherence, both in time and in space. Thank you very much.
Thank you very much for the inspiring talk. Now we have time for questions. Okay. Please go ahead.
I
Yes.
have a question.
Okay.
Do you have time operator in this formalism?
Yes, yes, that big T that we had there is an operator, definitely.
But it is constructed as a POVM VM
You can
operator
build
or
the
self-consistent.
the T is one. If you use the Hern construction, your T will become one of its POVMs. Yeah. Now, a question you might have is, there's a theorem that says that you can't have, if your Hamiltonian is bounded below, you can't
Yes,
have.
okay,
a
this
joint
Pauli theorem is clear.
Exactly.
Yeah.
So I thought you were getting at that, so I'll answer that. So yes, Pauli theorem holds, and it means that for a system that has a Hamiltonian bounded below, you cannot define a clock that will work forever. You'll have clocks that last a certain interval, and you'll have to use more than one of them to actually keep track of the evolution. That also answers another question that people normally have that say, well, but general relativity is a chaotic system, generically. When you try to build a clock out of observables in a chaotic system, your clock will go bad quickly. And the answer is yes. All these constructors are always for a finite amount of time. If you want to go longer, you have to introduce more clocks. And that is usually the case, right? Even a regular clock is only good for 24 hours. If you want it to go more than 24 hours, you have to introduce a second variable, the day of the month. And if you want to go more than a month, you have a third variable and so on. So that's a very common occurrence when you talk about clocks.
Okay.
Okay, further questions, please?
Can I have one question?
Yes.
So my question is, so you have used the almost classical clock for your calculations with,
Yes.
let's say, second order expansion. Will you also get Linblad type of operator in your evolution equation if you took into account the higher order, let's say,
Yes.
expansion?
Yes, you get successive commutators with a Hamiltonian.
Okay, so you still pertain the same type of equation, right?
Right, provided your P of TT is of the form I was assuming there, right? I was assuming, remember, delta plus delta prime, delta second, etc. If you keep that one, you get the Linblad with a Hamiltonian for all terms. If you put a P of TT that is some function, well, you're going to get something on the right-hand side, and it's not going to have a simple form.
Okay, thank you.
Next questions, please. Comments, remarks? I can't hear any. So in that case, many thanks again, George, for your great talk.
Thank you all for the invitation, and again, thanks for accommodating my time.
You are welcome. So we close the meeting, and goodbye to everyone.